So in this session, we will study the fundamental physics for evolution of stars. So first topic is elementary physics in stars. And the second topic is nuclear reaction in stars. The first topic is elementary physics in stars. A star is composed of a number of ions, electrons, and photons. So as we estimate the average temperature of a star's temperature is high enough to remove electrons from atoms. We have to consider the ions and electrons and the photons. We need to familiar with the property of ion and electrons. And also the photons. Light is another important element to form our stars. So we have to be familiar with also the property of photons. So by understand the property of gas and radiations, we could write down the equation of state. Pressure of a star is a function of the density of rho and the temperature of T and the mass fraction of X. So we understand the property of the gas and the property of the photons. But these two elements interact with each other. Also have to be familiar with the interaction between the gas element and the photons. So we have three types of the interactions of the gas and the photons. First one is the gas absorb the photons to change the energy state from the lower energy state to the higher energy state. And also the gas emit the photons, transition from the higher energy state to the lower energy state of a gas. And the scattering. Photons approach to the gas and scattered. So we have to introduce these three processes of the interaction between the gas and the photons. First topic is the pressures. So to describe the equation of state, we have to be familiar with the pressures. So pressure is a force per unit area that is exerted on the wall. So in this situation, the gas is moving inside of the cylinders and the gas molecule push the walls. So pressure is a force per unit area that is exerted on the wall. The force per unit area is equal to the momentum transferred per unit time per unit areas from gas to the wall. So if you remember the equation motions, equation motion is expressed derivative of momentum with respect to time equal to the F. So if you divide the area of the S is the area. Right hand side is equal to the pressure. So because the force divided by the areas, it becomes pressure. And the right hand side is momentum transferred. Momentum transferred per unit times per unit areas from gas to the wall. So we'd like to calculate left hand side to find out the pressures of gas element. Okay. First of all, we'd like to check if we could use the ideal gas assumption. So ideal gas means Coulomb interaction can be ignored. We have protons, major important element to form a stars. So it has a positive charge. And the electron has a negative charge. So positive charge and the negative charge, the attractive Coulomb force is acting between these two particles. But if we consider the positive charge, another protons, then repulsive force is acting between these two protons. So we have to check if we need to take into account these Coulomb force into account when we study the evolution of stars, or we can ignore these Coulomb interactions, then mean particle distance can be calculated. So if you consider the box of the D, so we'd like to calculate the mean distance of the D. So in this situation, we could find a single particles inside of this box. So if you consider the same size of the box next to this box, size of the D, again another particles. So this means number density of the N of the N times the D cube is 1. So from this equation, D is the mean particle distance. So mean particle distance can be calculated from the number density of the N. Okay, so D is calculated N to the minus 1 over 3. Okay, and N is the number density is calculated density divided by the mass numbers times H, atomic mass unit. So you can substitute this N is here, but we need to find the rho. Rho is the density. Rho can be calculated. Mass over stars divided the volume. Volume is 4 over 3 pi r cube. So m is the mass of stars. And the r is the radius of a star. Then you could calculate the density. Then substitute here. Then once you have a N, you can substitute here to find the D. So you could calculate D is A m sub h over rho 1 over 3. And you can substitute rho is here. It becomes 4 pi over 3 A m sub h over capital M 1 over 3 r. R is the radius of the stars and M is the mass of the stars. Okay, so we have this equation, mean distance between the particles. So using this mean distance between the particles, you can estimate the Coulomb energy between the two particles. So we consider the ions with a positive Ze, positive charge, and another ion is positive Ze charge. And then repulsive force is acting between these two particles. The Coulomb energies estimated 1 over 4 pi epsilon naught d square e square over d. D is the distance between these two particles. And the kinetic energy is expressed kT. Then kT can be calculated with the Villiers theorems when we studied average temperatures. We derived this equation using the Villiers theorems. So alpha over 3. mg is the mass of the gas element. G is the gravitational constant. M is the mass of the stars over the R. R is the radius of the stars. Then we could compare these two energies, Coulomb energy and kinetic energy. kinetic energy is a translational energy of the particles. Then take a ratio. If you take a mass of the star is a solar mass, is 1.4 times 10 to minus 3. So this is really small numbers. Then Coulomb energy is much smaller than the kinetic energy. So this means we don't have to take into account the Coulomb interaction. So we can safely use the ideal gas assumptions. Okay, this is the end of this session.